back. Pass that back.
George, when's your birthday?
Well, I was looking at last year's schedule and realized that, well, I had copied last year's syllabus and essentially just changed the exam day to modify to the corresponding exam day this year. But I realized that last year I delayed the exam. So I'm going to give you guys an option. There's two options for exam one. You can either take it Wednesday or Friday, but if you take it on Friday, it will cover more. Okay? Do you have a preference? So I'll only go through the end of chapter 2 if you take it Wednesday. Today's Friday. Wednesday of next week. Or if it is Friday of next week.
Wednesday.
Okay. Okay, we'll go for Wednesday.
Unless you want to push it Friday and just do it.
No.
What is the homework schedule like next week then?
Just journal stuff for sure through Wednesday, and probably even on Friday there'll be nothing different.
So we'll have something to turn on Monday though.
No, in fact, if you look on Moodle, I put it there yesterday. It's just journal stuff. Okay, so yeah, I will typically give you a little cushion before exams to work on your journal if you're behind. Once we get past chapter 2, then it's going to be about half the problems to do for your journal for the completion.
Are you just baiting us because you know the test is going to be really bad?
The test is the test. It's going to be similar to old tests.
No homework, guys.
If you look at those old tests and say that's bad, then I guess for you it's bad. All right. So once again, let me start by focusing on big picture stuff, talking about the main facts to know, and maybe hinting at proofs you should know. And then the last part of class, we're going to focus on a special kind of example related to recursive definitions of sequences. We're going to iterate functions and think about what happens with what's called the quadratic family. All right, so we have the definition of a convergent sequence, definition of what it means to diverge to infinity. By the way, I think I know why the book calls it converge to infinity, because they didn't want to allow themselves to write things like this. Equals infinity, even though infinity is not a number. But I say, even if you say a sequence diverges to infinity, again, an example being like that, or like this, or even natural log of n, those all go to infinity. I say diverge to infinity to emphasize that they are diverging sequences. You can still write that. So this is going to come up and be relevant near the end today. You can still write this even when your sequence diverges. In particular, if it diverges to infinity, that's the case where you would write this kind of thing, when it gets eventually above any number. And we wrote that definition down the other day. You should know algebraic properties of sequences, of course, and the squeeze theorem. Here's another property in section 2.1 that you should know. If you've got a sequence that's in a closed interval from A to B, and if it converges, then the limit is going to have to be in that closed interval. It's not true for open intervals, right? If you've got an open interval, like the open interval from 0 to 1, for example, and you let xn equal 1 over n, that will generate a sequence that converges to 0, but 0 is not in the open interval from 0 to 1. So it's a special property of closed intervals that distinguishes them from open intervals. We have this very important fact. A monotone sequence converges if and only if it is bounded. You should be able to prove that for the test. I have put that on other exam ones. The proof being on page 61. They do it for the case of a monotone increasing sequence. Maybe, for your exam, I'd have you prove it for a monotone decreasing sequence. But a monotone decreasing sequence, that's bounded, I forgot to say. Well, okay, excuse me. A monotone decreasing sequence converges if and only if it's bounded below. That could be a proof on the test. They use the completeness axiom. For their monotone increasing sequence that they assume is bounded above, they show it converges, it has to converge to the sup. Not of the sequence. You don't say the sup of the sequence, you say the sup of the outputs of the sequence. Since the sequence is bounded above, the set of outputs is also bounded above as a set, so it will have a sup. And even though the completeness axiom is stated in terms of sups, if I had you prove that monotone decreasing sequences converge if and only if they are bounded below, you could take it as an axiom that when you have a set that's bounded below, the inf will exist. You wouldn't have to prove that from scratch. Though you could, there could be a proof, I mentioned this before, that shows you could prove that from the completeness axiom, but it would be separate from the proof of this theorem in the case where you have a monotone decreasing sequence. You could even generalize the theorem to say an eventually monotone sequence converges if and only if it's bounded. I haven't said what eventually monotone means. It could be a definition on the exam that you have to decide what a good definition would be, even if it's not in the book. And it's not in the book. So you'd have to decide to think about that. That could be a problem to say, give me a good definition for what an eventually monotone sequence would be. Cauchy sequences and the Cauchy convergence criterion. Let's write up the definition of a Cauchy sequence again. A sequence xn, and again, our book uses the curly braces to refer to the whole sequence, and you should too. Don't just write xn without the curly braces. Is a Cauchy sequence if for all epsilon greater than 0 there exists a capital N, a natural number, such that the distance between terms in the sequence can be made less than epsilon, as long as both little n and little m are sufficiently large, bigger than or equal to the capital N you found. The book does an example that I'd like to go over. An example of verifying that something's a Cauchy sequence where the sequence is generated with a summation. Here's the example they do. Let A sub n equal the sum, as k goes from 1 to n, of 1 over k squared. Okay, so think about what that means. That means A1 would be 1 over 1 squared is 1. A2 would be 1 over 1 squared plus 1 over 2 squared is 1 plus 1/4, 5/4. A3 would be 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared. 1 plus 1/4 plus 1/9. Okay, I'll add the fractions here. Hopefully I won't make a mistake. Common denominator of what? 36? 36 plus 9 plus 4 over 36. That's 49 over 36. Etc. Did I do it right? Add my fractions right? Okay. You've seen this kind of thing before in Calc 2. You should have seen it. Do you know what these are called? This sequence? It's the sequence of something related to this sum. Remember what it's called? sequence of partial sums, they're called. Does that ring a bell? Does it have a limit? It's not clear. We could gather numerical evidence to see if it seems like it has a limit, but numerical evidence is never approved in this kind of situation. It's related to the infinite series, where you let k go to infinity. Does anybody remember if that converges or not? Anybody remember? It does. It's called a p series with p equal to 2, and when p is bigger than 1, you get a convergent p series. It converges. How could you prove that converges? You could prove it converges by proving that this sequence has a limit. In fact, by definition, this converges to whatever this sequence converges to, if it does converge. But how are you going to show it converges if it's not clear what the limit is? You can use the Cauchy convergence criterion. You can show it's a Cauchy sequence, and the theorem, the Cauchy convergence criterion, says that a sequence of real numbers converges if and only if it's a Cauchy sequence. It's not too hard to show it's a Cauchy sequence. Let's come way over here. Can you turn the camera way over here? Let's just do a little scratch work to convince ourselves. This scratch work is in the book. I'm just mimicking what the book does here. Assume, we'll say n is bigger than m, and consider a sub n minus a sub m. Let's not worry about absolute values. This would be positive if n is bigger than m, because I keep adding positive terms over here. That can be thought of as a summation. If you think about it carefully, k goes from m plus 1 to n. Why? Well, because if you write it out, it's 1 plus 1/2 of 1/2 squared plus 1/3 squared, etc., plus 1 over n squared minus 1 plus 1 over 2 squared plus 1 over 3 squared, etc., plus 1 over m squared. And I'm assuming n is bigger than m, so somewhere back in here, in this summation, there was a 1 over m squared in there. So everything up to that point cancels with everything down there. And you're left with whatever is left over there, which would start with 1 over m plus 1 squared. And in this case, that is, I probably should have just plugged in what AK was right away here. It was this. As always in real analysis, it's often a good thing to take something and say it's less than something else that might be easier to work with. Now, this seems like it could be easy to work with, but it turns out it's not clear what to do here. And it's easier to say that this is less than the following summation. Replace k times k with k times k minus 1. It's not the same summation, it's a different summation, but it's bigger. I'm dividing by something that's smaller. Makes the fractions bigger, it makes the summation bigger. That seems like it could be harder, but it actually is easier because you can now use partial fractions to write this in a special way. If you set it equal to a over k plus b over k minus 1, this is probably the most mysterious step in the book. They didn't tell you to use partial fractions. The author didn't. Set that equal to a plus b, a over k plus b over k minus 1. Solve for a and b. Quick little trick is just to multiply both sides by k times k minus 1 to get 1 equals a times k minus 1 plus b times k after cancellation. Just focusing on these fractions here, I multiplied both sides by k times k minus 1. If k is 0, this term goes away and forces a to equal -1. k is 0, this becomes a -1. To make that equal 1, a would have to be -1. And if k is 1, this term goes away. You're left with b times 1 equals b 1. b would have to equal 1 to make it true. So what this means is I can now replace that fraction with that. Oh, like I made a mistake. Anybody see a mistake? No, I guess it's okay. Once again, we're sort of at a point where it's not clear what to do. I mean, it's not clear that this was going to work to begin with. But it actually is a good thing, because if you now write this out, it's called a telescoping sum, and a bunch of stuff cancels. When k is m plus 1, this becomes 1 over m minus 1 over m plus 1. When k is m plus 2, the next value, this becomes 1 over m plus 1, and this becomes 1 over m plus 2. When k is m plus 3, I get a 1 over m plus 2 minus 1 over m plus 3, etc. It's not really a proof, but you shouldn't really use dot, dot, dots in proofs, but we'll be okay with it here. When k is n, I get 1 over n minus 1 minus 1 over n. Maybe I should consider the second to last case as well. When k is n minus 1, I get 1 over n minus 2 minus 1 over n minus 1. A bunch of stuff cancels. This cancels with that. This cancels with that. This cancels with something else that comes next, etc. This doesn't cancel. This cancels with that. This cancels with something else. What am I left with? I'm left with 1 over m minus 1 over n. Which is less than 1 over m, which can be made less than any given epsilon by choosing m sufficiently large. If this were scratch work, you'd probably want to write want. So what would the proof look like? Don't forget your stamp. Let epsilon greater than 0 be given. You got to show it's true for all epsilon. By the way, one big thing in the last couple of homeworks that I graded here is that instead of using the stamp and just saying let epsilon be greater than 0, people are restating the definition without really saying to choose the capital N based on the given epsilon. You're just saying, well, I must show for all epsilon greater than 0 there exists a capital N. I mean, it's not bad to say that, but then you should next say let epsilon greater than 0 be given and work with a fixed epsilon, a fixed arbitrary positive epsilon, to find a particular fixed capital N that you know will exist. So I typically make comments about that. So you should make sure you're looking for those comments and try to do what I tell you to do on the exam. So you'd say let epsilon greater than 0 be given. You'd say choose capital N so that 1 over capital N is less than epsilon. Assume little m and little n are bigger than or equal to capital N. Without loss of generality, assume little n is bigger than little m. You get away with greater than or equal to. It's okay to assume that little m is strictly greater than little m. And then go through all this stuff. Mm-hmm.
Are we always going to have 1 over big N less than epsilon?
No. Sometimes you want to choose and capital N so that 2 over big N is less than epsilon or something like that. So it's not always so simple. in your choice of capital. Anyway, this would end up proving that this sequence is a Cauchy sequence, and therefore by the Cauchy convergence criterion, it converges, which means this infinite sum converges. Doesn't tell you what it converges to, though. Did I show you what it converges to? Already I forgot. It was either this class or my Calc 2 class. What does it converge to? I think I have it in here somewhere. Oh, I think I have it. Mathematica, tell us, what does it converge to? Pi squared over 6. Well, of course. Duh. What? Pi squared over 6. Pi? Where'd the pi come from? I don't see any circles. Pi? Really? It took Euler's genius, Euler lived in the late 1700s, to figure this out, that it equaled pi squared over 6. Newton and Leibniz, geniuses that they were, could not figure it out. The Bernoullis could not figure it out. Euler figured it out. And in Foundations of Math, in your Journey Through Genius book, you'll read about how Euler did it. Actually, to figure this out, Euler used infinite products instead of infinite sums. Whoa. I mean, he had to relate it to the infinite sum. But his technique was to use infinite products and the sine function particularly. What if I change p to some other number like 10? What do I get? Pi to the 10th over 93,555. Wow. How about I change the power to 100? Whoa. Something, a rational number times pi to the 100. Wow. It's a rational number times pi to the 100. And Mathematica did it in a couple seconds. How? What if it's 3? Oh, zeta of 3. It turns out when it's an even power, like 2, 4, 6, 8, etc., it can be done in terms of a rational number times the corresponding power of pi. But if it's an odd power, there's no simple way to write it in terms of I, but it's given a name. It's called zeta of that number. Zeta of 3, zeta of 5 here. What is zeta? It's called the Riemann zeta function. It is an honest-to-goodness function. I mean, you can approximate zeta of 5, for example. Zeta of 5. Come on. About 1.03693. It's a very important function. In fact, it's related to the most famous unsolved problem in math, the Riemann hypothesis. If you solved the Riemann hypothesis, you would be world famous. I think there's $1 million prize for solving it.
What is it? We're up for time.
Just a second here. What if P is 1? That diverges, you should know. That's the harmonic series. Remember that. What's the what's the Riemann hypothesis? It's pretty weird sounding. Oh, here we go. It's related to complex analysis. We're so excited. It's a conjecture, meaning it's a thing that people think is true, but it hasn't been proved or disproved. That the zeta function, the Riemann zeta function, has its zeros only at negative even integers and only at the complex numbers with real part 1/2. What? That's the hypothesis? Why is that such a big deal? That's the most famous unsolved problem in math. You might wonder, why is that such a big deal? Why would you care about the zeros of the Riemann zeta function?
Have you given it a shot?
I have not, no. It's actually of fundamental importance because it tells us information about the distribution of prime numbers through a way I won't explain. And prime numbers, you should know, are not just good for factoring, they're also good for cryptography, secret codes, and making your internet transactions secure. So maybe the security of your internet transactions ultimately depends on the truth of the Riemann hypothesis. I'm not sure about that. Maybe. Wow. Certainly it's related to distributions of prime numbers, they say that here. And prime numbers certainly are important for cryptography, especially knowledge about really big primes, which we're generating new really big primes all the time, and it's good to know we'll never stop generating new really big primes because the number of primes is infinite. Euclid proved that over 2,000 years ago, and it's one of the most beautiful proofs there is. It rivals the proof that the square root of 2 is irrational in beauty. You can prove it in about 5 sentences. Profound fact about the universe, there are infinitely many primes. And we can be thankful to God for that because, again, it makes our internet transactions secure. Though you should read about quantum computing. Ever seen any articles about quantum computing? Google's trying to create what's called a quantum computer, and other people are trying to create one too. And they say if they create a quantum computer, it's going to be able to crack all the codes. People are desperately trying to find new coding systems, though, so that a quantum computer can't even break it.
Why?
Because they're just dumb, and they want to push the envelope. Actually, if you came up with some sort of algorithm that could crack any coding system, whether or not you had a quantum computer, probably your life would be in danger. Probably the government would abduct you. Or maybe the Chinese would abduct you and you'd never be seen again. Okay? So, I don't know, just, yeah, that's a word of warning. There are bad things that could happen to you if you know too much. All right, on to subsequences in the Bolzano-Weierstrass theorem. We're stating the Bolzano-Weierstrass theorem in kind of its simplest form. It has a generalization to n-dimensional space. If you do say the theorem name fully, you do say, please say Bolzano-Weierstrass, not Bolzano-Weierstrass. Delete that from your mind. You could call it the BZ theorem, I guess. Isn't there a GZ theorem in algebraic structure? Isn't there one? Like for a group G and its center Z? Around the center of a group.
That was a
Yeah.
Center of a group is also. The center of a group is also.
Bolzano-Weierstrass. Suppose Xn is a sequence in the closed interval from A to B. In the closed interval means all the terms are inside that interval. Then, nothing about a monotone sequence here. Xn has a subsequence that converges to a number in that same closed interval. It has a convergent subsequence. I only hinted at what subsequences were last time. Let's give a more formal definition of a subsequence, of a given sequence. It's more than just that the terms are a subset of the set of terms of the original sequence. The terms have to occur in the same order, so it's like you're taking the original sequence and just taking some of the terms to create a new sequence, but those terms have to occur in the same relative order. Given a sequence xn and a strictly increasing sequence P sub n of positive integers we say the sequence x sub P sub n, double subscripts there, is a subsequence of the original sequence. Okay, kind of confusing, I think, when you first read it. It's best to think about it in terms of examples. And perhaps best to think of it in terms of lists, thinking of sequences as lists. You got a sequence x1, x2, x3, x4, etc. There's infinitely many subsequences. You could pick, for example, the terms with odd subscript. The P sequence in this case would be 1, 3, 5, 7, 9, 11, etc. That would be a strictly increasing sequence of positive integers. You could pick just the even subscripts. The P sequence in that case would consist of 2, then 4, then 6, then 8, then 10, etc. You could pick prime subscripts. You could pick Fibonacci number subscripts, although you'd have to technically, the first two Fibonacci numbers are both 1, so you'd have to exclude the first one. Right? The Fibonacci sequence goes 1, 1, 2, 3, 5, 8, 13. You know how to make that? Any term is the sum of the previous two terms. But it starts with two ones. You'd have to exclude the first one because then it would be strictly increasing if you didn't. Exclude the first one and jump to x2, then x3, then x5, then x8, then x13, then x21, then x34. Fibonacci sequence, except for the first one. So does that help? Thinking about examples like that helps you see what this means. So now come back to the theorem. Every sequence in an interval, monotone or not, this is more significant for non-monotone sequences, has a subsequence that converges to some number in the interval. You might say, well, big deal, who cares? Do you really care if there's a subsequence that converges? Yes, we will see, starting in chapter 3, there are important theorems that are reliant on this theorem for their proof. Maybe you generate a sequence in some way in the proof of the theorem, but you're not sure, it's not necessarily monotone, so it doesn't necessarily converge even if it's bounded. But if you know it's got a convergent subsequence, that means there is some sequence that converges. You can say there's some sequence that converges in this interval. And that ends up being important. Mostly for proofs of other theorems. You know, a theorem is useful to a mathematician if you can use it to prove other theorems, right? That's useful. Not the ordinary kind of definition of useful to most people. But to a pure mathematician, theorems are useful if you can use them to prove other things. Okay, I think I'm going to jump ahead to these last two things you see here. Introduce the idea of a Limsup and a Liminf. Combining limits and sups and limits and infs. That sounds scary.
Yes.
It is a tough topic. I'm just going to introduce it today. You'll be reading about it if you haven't yet. and doing homework problems related to it that are journal problems, so you can check the answers with my key. We'll think about examples here. And then, hopefully I'll also have a little time at the end to go back to our counterintuitive example and think about some interesting recursively defined sequences. What is a Limsup and a Liminf? Let's consider an example here. So here, A of n, or in our notation, A sub n, is n over 3 minus the floor of n over 3. Floor is Mathematica's version of the greatest integer function. So in the book, in fact, I took this example as one of the homework problems in the section from the book. I think it's one of your completion problems. The book writes it like that. Seen that kind of thing before? For example, A of 4 is 4/3 minus the floor of 4/3. The greatest integer in 4/3 is 1. It's less than 4/3. It's the greatest integer less than 4/3. Less than or equal to 4/3. So this is 4/3 minus 1 is 1/3. Discrete plot will plot the values of this sequence, and here they are. This is not bouncing back and forth between two numbers. It's cycling through three numbers. First, 1/3, then 2/3, then 0, 1/3, 2/3, 0, 1/3, 2/3, 0, 1/3, 2/3, 0, etc. This has got three different numbers that can be limits of subsequences of the sequence. 0, 1/3, and 2/3. 0 is a limit of a subsequence.
Sorry,
The sequence x3, x6, x9, x12. I don't actually have to stay on multiples of 3 all the time. I could jump up to x13, then come back down to x15, x18, x21. The simplest subsequence that converges to 0 is the one that stays 0 all the time. The subscript is a multiple of 3. x1, x4, x7, x10, x13 would be a subsequence, the simplest subsequence that converges to 1/3. x2, x5, x8, x11, x14 would be the simplest subsequence you could think of that converges to 2/3. There are three different possible numbers that are limits of subsequences of this. Just like with -1 to the n, bouncing back and forth between -1 and 1, there are two numbers that can be limits of subsequences, 1 and -1. It's a theorem, it turns out. This is not a definition, but a theorem, that the limit superior, the Limsup, of the sequence is the supremum of the set of all possible subsequences. Excuse me, the set of all possible limits of subsequences. And the limit inferior, Liminf, is the inf of the set of all numbers that are limits of subsequences.
So pretty
So-
often, are those the same as just the super, or more times than that?
Let me just say the theorem here, so I don't confuse you. It's easiest to think about in the case of a bounded sequence. So this is not a definition. I haven't told you the definition yet. Okay, so this is a bit backwards. Let xn be a bounded sequence. And by the way, if it's a bounded sequence, what would Bolzano-Weierstrass tell us about that? It's got a subsequence that converges to something. Bounded means it's going to be inside some closed and bounded interval. and let S equal the set of all numbers x such that there exists a subsequence of xn converging to x. S is the set of all numbers so that there exists a subsequence of the sequence converging to x. Different sequences produce different s's. It's not empty because the sequence is bounded. There will be at least one subsequential one.
So in this case, S would contain 1/3, 2/3, and 0.
Yep, just 3 points. 1/3, 2/3, and 0. Then it turns out this thing called the Limsup. It's traditional to write as n goes to infinity of xn is the sup of S, and the Liminf of the sequence is the nth of S. This is not a definition, it's a theorem. Okay, but let's still avoid the definition for the moment, because the definition is pretty tough.
Are those xn's then out of brackets?
Yeah, when you use limit notation like that, you don't need the braces.
Okay, but it still represents the sequence.
It's the terms in the sequence, yeah. It's the notation we use when we use the limit symbol. Let's consider these other examples. How about this one? an is -1 to the n times 1 plus 1 over n. What's a discrete plot of that look like? It looks like this. So this is not bouncing back and forth between 1 and -1. It's not doing that, but the odd subscripted terms, x1, x3, x5, x7, x9, etc., are approaching +1. And the even subscripted terms, x2, x4, x6, x8, x10, etc., those are approaching -1. Or do I have my odds and evens mixed up? Oh, it's the other way around. These are the even ones. This is x2, x4, x6, x8, etc. x1, I didn't see it here, it's down there, -2. x1, x3, x5, x7, x9, etc. I hope it's intuitive that because of that, there are two numbers that are limits of subsequences, 1 and -1. S is a 2-element set, 1 and -1. The inf of S is -1, the sup of S is +1. The lim inf of the sequence is -1, the lim sup is +1. On to the next example. This one's tougher. Well, in fact, it's not a bounded sequence to begin with. Let me make it a bounded sequence. Let's consider a different example, actually. Let's just do sine of n. So a sub n is sine of n. Points are bouncing all over the place. Is the graph of sine of x in here anywhere? Well, we're starting with sine of 1 when n is 1. So I guess that's sine of 1. The graph of sine of x is kind of going up like this and down like that, then up. But we're only plugging in integer values of n, positive integer values. It's a bounded sequence. It's stuck between -1 and 1. It's got to have a convergent subsequence, but it's not clear how to pick the subscripts to make a convergent subsequence. If I were to try creating a subsequence that converges to positive 1, for example, I might let that be, consider x1 to be my first term, then x2, then skip ahead to, let's see, 3, 4, 5, 6, 8, to x8 is a bit closer to 1. Then skip ahead to the next one that's even closer to 1. Maybe this one is a little bit closer to 1. Then maybe that one's a bit closer yet. Then maybe that one's a bit closer yet. It's hard to tell. For me to tell. Do these ever equal 1? No. Because if they equaled 1, n would have to be equal to pi over 2 plus some integer multiple of 2 pi, and that can't happen. So it's never going to equal 1 here. But I hope it's somewhat intuitive that perhaps you could get arbitrarily close to 1. 1 is a limit of some subsequence. That can be proved, though the proof is difficult. In fact, get this. Any number between -1 and 1 is a limit of some subsequence. There's uncountably many numbers between -1 and 1. I guess there are uncountably many subsequences of any given subsequence. And there's uncountably many of them that converge. Weird. I get that, there's actually uncountably many that don't converge as well. There are plenty of subsequences that don't converge. The original sequence itself doesn't converge. Any number between -1 and 1 is a limit of some subsequence. S is the entire interval from -1 to 1. Its inf is -1, its sup is 1. The Liminf is -1, the Limsup is 1. This one looks like that. It's not a bounded sequence, so technically this theorem does not apply. Though if you consider the supremum of a set that's not bounded above to be infinity, and the inf of a set that's not bounded below to be negative infinity, maybe it would make sense to say the Limsup of this is infinity and the Liminf is negative infinity. And yeah, if you want to, you can do that. And the book does talk about it. Actually, it's a little weird. The Liminf can actually be positive infinity and the Limsup can actually be negative infinity. For that example, both the Limsup and the Liminf in this extended sense are plus infinity. The sequence doesn't have a limit. It diverges to infinity, I say. The book says converges to infinity. So in that extended sense, the lim somehow S is the point consistent with just infinity. No, don't think that way. Just essentially by definition, the Limsup and Liminf of this are both infinity. And if I put a negative sign in front of the n, then the Limsup and Liminf are both minus infinity. It is a very important fact that if the sequence converges, if that's a convergent sequence, the Limsup and the Liminf are equal to each other. Now, what do you think they equal if this is convergent? Only one number they can be. They equal whatever this converges to. Because that one number is the only limit of the sequence, and it's actually also the only limit of all possible subsequences. And in fact, all subsequent sequences will converge to it on top of that. These things are all mentioned in section 2.3. What are Limsups and Liminfs good for? We won't really need them until chapter 6. Oh, you're kidding me. So why are they introduced here in chapter 2? Because they're related to sequences. They're related to facts about sequences. You might wonder, does this summation converge or not?
I was thinking about that last night.
You were? All right. Does that summation, does that infinite series converge? Mathematica says it does. Says it converges to 5/3, but how would you prove that? It turns out an extended version of the ratio test and or the root test that you may or may not have learned about in Calc 2, you should learn about them, can be used to prove them, and that extended version involves Limsups and Liminfs. I think I better not say more. In chapter 6, I'll tell you what page it is. Chapter 6, pages 223 and 224 are theorems, the ratio test and the root test, that are more general than the corresponding theorems you had in Calc 2 that can be used to prove this series converges, and they involve Limsups and similar statements, which makes them stronger theorems. All right, I think I'm just going to skip the definition of Limsup and Liminf for today, but you'll be reading about it. I want to end class by considering an example, an important kind of example. We've considered this, the counterintuitive example here already, iterating this function. Let's consider a generalization of that. This family of functions right here. F sub mu equals f sub mu of x equals mu times x times 1 minus x, and consider sequences that are generated by this recursive equation. X sub n plus 1 equals f sub mu of x sub n. Our counterintuitive example fits this when mu is 4. Remember the 4s were in it? And that was a chaotic example. Kind of like sine over n is seemingly chaotic too. That chaotic behavior does not occur for all values of mu, however. When mu is 0.1, for example, and you give me a seed, an x0, or you could call it an x1 of 0.9 is what I took here, then this graph illustrates that the sequence converges very quickly to 0. If you plug in 0.9 to the red graph, go up to the red graph from the x-axis here, the output's close to 0. These black lines are indicating you could start at the point on that blue line, which is y equals x, up at 0.9, comma 0.9, and go down to the red graph. The output is close to 0. If you go over to the blue graph like this, you're now at a point whose coordinates are both very close to 0. Both of those numbers are the same, and they are the output of this function when you plug in 0.9. If you go back down to the red graph here, that corresponds to plugging in that small number into the red graph, giving you an even smaller number, even closer to 0. This is generating a sequence that converges to 0. It's a bit hard to see, though. If I increase n here, you don't really see much. I think if I go up by 1, you'll see a little bit here, maybe. Look down there and let's see if we see anything. Yeah, did you see that?
Oh, yeah.
Watch right there. Here we go again. 1, 2, 3, go. It's stepping down. It's getting closer and closer to 0. This is called a Cobweb plot for reasons I'm not going to get into at the moment. That's when mu is 0.1. What if we increase mu, make the red graph steeper? What if mu is 0.936? Does the sequence still converge to 0? Yeah, you can see it like a staircase there. And the sequence is converging to 0. Again, the blue line is the line y equals x. Anytime this black line is on that line, the first and second coordinates are equal. The first coordinate of this point and the second coordinate is 0.9. The second coordinate at this point is the output when you plug in 0.9. Going over to the blue line gives you the point with the same coordinates. And then going back down to the red gives you the output of the function when the input is whatever the coordinates of this are. And because of that, you can continue in the staircase fashion, and you see you're sort of forced to head to 0. But what if we increase mu even further? Then the red graph has a slope bigger than 1 at the origin, and watch this. The sequence does not converge to the origin, it converges to where the red and blue graphs cross. Staircase. What if mu is up even further? Weird things start to happen. You get some spiraling. Cobweb, yeah, that's what's called the cobweb plot. Oh, and then like a hallway or something. And then it's just sort of all over the place. So different mu's give you radically different behavior in the sequence. In this case where mu is 4, which is this last value up here, the points are jumping all over the place, though you can understand why the outputs are the way they are with this diagram. And it turns out that sequence also fills the interval from 0 to 1 densely, so to speak. The set of all possible limits of subsequences is the entire interval for this as well. Okay? But in some situations, at least if you start your seed small enough, for example, like if mu is, if I start at 0.1, and mu is, say, between 1 and 2, that generates a monotone increasing subsequence, or sequence, that's got to converge. And next Monday we'll figure out where it converges to, what it converges to. We'll talk about the definition of Limsup and Liminf, and we'll review for the test.
Flip.